If you're the type of person who sometimes wakes up at 3 a.m. and lies in bed trying to wrap your tiny mind around the achingly vast universe and where it's all headed, well, we have something for you. Ever since the Big Bang, the universe has been drifting and expanding. The birth and death of stars leave an aftermath of galaxies, planets, and even living organisms. This includes the sun, planets, and our solar system. At the center, the sun swept in smaller elements like hydrogen and helium. Farther away, heavier elements formed planets. Based on the core accretion model, gravity was the driver, coalescing Earth from a cloud of dust. Though Earth was neatly orbiting the sun as a rocky mass 4.5 billion years ago, no organism could survive there. Radiation from the recent supernova kept the planet extremely hot, its surface molten, and oxygen was non-existent. Plus, incredibly massive meteorites and asteroids frequently slammed onto the surface. The Earth got so hot it began melting. Heavier material sank to the bottom. Lighter stuff rose to the top. Some elements evaporated. This transformation created the Earth's layered core and mantle, crust, atmosphere, and magnetic field. Without it, Earth would be blasted by harmful rays from the sun. But before we jump into our time machine, make sure you click the subscribe button and turn on notifications to be one of the first to watch our videos. In the late Hadean Eon, the Earth was still in its late bombardment stage. There is no life. Temperatures are extremely hot, with frequent volcanic activity and hellish environments. The atmosphere is nebular, possibly early oceans or bodies of liquid water. The moon is formed around this time, probably due to a protoplanet's collision into Earth. In addition, there's reason to believe that these collisions could have sparked the chemical building blocks for life, DNA. Eventually, the climate on Earth became more stable. Instead of a molten state, the Earth started to cool down. Water vapor condensed to form oceans, and the Earth cooled down enough to create continents. Vale-Barra became Earth's first supercontinent. Photosynthetic organisms appeared between 3.2 and 2.4 billion years ago and began enriching the atmosphere with oxygen. Single-celled organisms consumed the sun's energy. As a waste product, this cyanobacteria eventually filled the oceans and atmosphere with oxygen. Earth now had an oxygenated atmosphere for new life to flourish, but it wasn't cyanobacteria. Oxygen was toxic for them. Much life on Earth probably died out as its levels rose in what is known as the oxygen catastrophe. Imagine a dominant species polluting the planet until extinction. Resistant forms survived and thrived, and some developed the ability to use oxygen to increase their metabolism and obtain more energy from the same food. At this time, methane was more abundant in the atmosphere. One thing that methane did very well was trap heat in the atmosphere. It's one of the most efficient greenhouse gases. So when oxygen combined with methane, it produced carbon dioxide. All of a sudden, the greenhouse effect wasn't as strong. As a result, the whole planet froze. It was Snowball Earth for the next 300 million years. As oxygen filled the atmosphere, Earth's ozone layer thickened. Before the presence of an ozone layer, life was restricted to shallow water. Because water shielded harmful radiation, that's where life existed. Eventually, a thicker ozone layer enabled life to diversify on land. 541 million years ago, hard-shelled invertebrates originated in the oceans, and life got more diverse from there. Next came the age of fish, when thousands of fish species arose. Plants and fungi were the first to venture out of the water, requiring them to adapt to new conditions on dry terrain. Some fish stayed in close proximity to land and gradually adapted to life there, simultaneously developing lungs. Amphibians were the first vertebrates to make the move to land. The transition to life on land benefited these creatures because there was no predators to begin with, and food was plentiful. That was the start of the age of amphibians. Then, 250 million years ago, was the Permian extinction, which caused extinction of 95% of all living species. When Earth's climate became hotter and drier, rainforests collapsed, triggering the age of reptiles. Unanimously, depicted by Tyrannosaurus rex, locked in eternal conflict with mortal enemy Triceratops. Because reptiles evolved to dry land conditions, they gained a unique ecological advantage. Also notable is that Pangaea existed as one supercontinent in this era. Dinosaurs lived on one supercontinent. Plate tectonics were the mechanism that eventually tore continents apart. Don't forget that dinosaurs existed for 160 million years, so continental drift gradually rifted dinosaurs apart. From between the feet of stomping dinosaurs, ratty animals scurry about, cue an asteroid impact, and the age of mammals begins. Mammals evolved from mammal-like reptiles called therapsids about 200 million years ago, and birds from small theropod dinosaurs about 150 million years ago. This evolution of both mammals and birds accelerated after the extinction of the dinosaurs 65 million years ago, when a 6-mile-wide asteroid struck Earth just off the Yucatan Peninsula. This ejected vast quantities of particulate matter and vapor into the air that occluded sunlight, inhibiting photosynthesis. 75% of all life, including the non-avian dinosaurs, became extinct. Poor dinosaurs, imagine that if the meteor never hit Earth, we would be intelligent dinosaurs. The first true mammals evolved in the shadows of dinosaurs and other large archosaurs. When dinosaurs roamed the Earth, mammals were very small and were probably nocturnal to escape predation. And because dinosaurs went extinct, mammals emerged as the largest land animals at the time. Creatures like Ambulocetus took to the oceans to eventually evolve into whales, whereas some creatures like primates took to the trees. Then, just several million years ago, we believe that human life began to evolve. Apes remained in trees for their primary food source. Eventually, grass began to spread in places like the African savanna, and there were fewer trees. This forced apes to walk to new food sources. With their heads above the grass to see predators, apes evolved by walking on 2 legs. It also helped to have their hands available when they were traveling. Brain size increased rapidly, and by 2 million years ago, the first animals classified in the genus Homo had appeared. They were known for sharpening objects with silicon rocks. They began to master the use of their hands and fingers. In the Stone Age, early humans had fire under control. This enabled them to cook their food, giving them more calories. Modern humans, Homo sapiens, learned to make more complex sounds and share information in groups. They are believed to have originated around 200,000 years ago or earlier in Africa. The oldest fossils date back to around 160,000 years ago. And since then, humans have struggled to survive, or maybe Earth has. 5 billion years to build the Earth, and only several years to ruin it. Imagining the future of humanity, our planet, and everything we hold dear in our corner of the cold, dark universe is typically the domain of science fiction, and we're usually only worried about the next few hundred years at best. But what about millions and millions of years from now? What will happen then? Based on what we know about life, the universe and everything, some scientific predictions in fields like astrophysics and evolution can actually reach hundreds of millions of years ahead of our time. Let's have a look at what science says will happen in 1 Googolplex years from now. 1 million years from now, estimated shortest time by which humanity could colonize our Milky Way galaxy and become capable of harnessing all the energy of the galaxy. Earth will likely have undergone a supervolcanic eruption large enough to erupt 3,200 cubic kilometers of magma, an event comparable to the Toba supereruption 75,000 years ago. 10 million years from now, Earth is again the lush blue-green planet it used to be, full of life, animals, and forests. From the survivors of the Great Warming, a new explosion of life has been generated. There are again herbivores and carnivores, as well as large trees, even though none of them looks like the creatures which had populated the Earth before the catastrophe. 100 million years from now, Earth will likely have been hit by an asteroid comparable in size to the one that triggered the KPG extinction 66 million years ago, assuming it cannot be averted. 250 million years from now, all the continents on Earth may fuse into a supercontinent. 3 potential arrangements of this configuration have been dubbed Amasia, Novopangaea, and Pangaea Ultima. 1 billion years from now, if none of that gets us, the Sun will. Our home star bathes us in light and supplies the energy for almost all the life on Earth. But it won't be friendly forever. As we saw earlier, the Sun is gradually getting hotter. Eventually, it will be hot enough to evaporate all Earth's oceans and cause a runaway greenhouse effect that sends temperatures soaring upwards. As water evaporates from the Earth's surface, rocks harden, causing plate tectonics to slow and eventually stop. Pockets of liquid water may still be present at the poles or at high elevations, allowing small areas where life can survive. 2.3 billion years from now, the Earth's outer core freezes. If the inner core continues to grow at its current rate of 1 millimeter per year, without its liquid outer core, the Earth's magnetic field shuts down, and charged particles emanating from the Sun gradually deplete the atmosphere. 2.8 billion years from now, Earth's surface temperature, even at the poles, reaches an average of 149 degrees Celsius. At this point, life, now reduced to unicellular colonies, is isolated. Scattered microenvironments, such as high-altitude lakes or subsurface caves, will completely die out. 4 billion years from now, median point by which the Andromeda Galaxy will have collided with the Milky Way, which will thereafter merge to form a galaxy dubbed Milkomeda. The planets of the solar system are expected to be relatively unaffected by this collision. 5.4 billion years from now, with the hydrogen supply exhausted at its core, the Sun leaves the main sequence and begins to evolve into a red giant. 10 billion years from now, the Sun has expanded and it has become so large that it has absorbed and destroyed the Earth. Then it has collapsed into a white dwarf. The galaxy and the whole universe move slowly to extinction, with the running down of the energy generated by the primeval Big Bang. 150 billion years from now, the universe's expansion causes all galaxies beyond the former Milky Way's local group to disappear beyond the cosmic light horizon, removing them from the observable universe. 450 billion years from now, median point by which the circa 47 galaxies of the local group will coalesce into a single large galaxy. 1 trillion years from now, star formation ends in galaxies as galaxies are depleted of the gas clouds they need to form stars. 100 trillion years from now, all stars in the universe have exhausted their fuel. After this point, the stellar mass objects remaining are stellar remnants, white dwarfs, neutron stars, black holes, and brown dwarfs. 1 quadrillion years from now, estimated time until stellar close encounters detach all planets in the star systems from their orbits. The Sun have cooled to 5 degrees above absolute zero. 100 quintillion years from now, the Earth collides with the black dwarf Sun due to the decay of its orbit via emission of gravitational radiation. If the Earth is not ejected from its orbit by a stellar encounter or engulfed by the Sun during its red giant phase. 3 tredecillion years from now. The year is 30, followed by 42 zeros of our era. Estimated time for all nucleons in the observable universe to decay. By this time, if protons do decay, the black hole era, in which black holes are the only remaining celestial objects, begins. 6 duovigintillion years from now. Estimated time until a stellar mass black hole with a mass of 3 solar masses decays into subatomic particles by the Hawking process. 1 Google years from now. The year is 10, followed by 100 zeros. Estimated time until a supermassive black hole with a mass of 20 trillion solar masses decays by the Hawking process. This marks the end of the black hole era. 1 Googolplex years from now. Current data suggests that the universe has a flat geometry, or very close to flat, and thus will not collapse in on itself after a finite time, and the infinite future allows for the occurrence of a number of massively improbable events, such as the formation of Boltzmann brains. Eventually, matter itself is expected to come under the influence of radioactive decay, as even the most stable materials break apart into subatomic particles. The universe enters the dark era, in which all physical objects have decayed to subatomic particles, gradually winding down to their final energy state in the heat death of the universe. What do you think? We'd like to hear your opinion in the comments, and don't forget to subscribe.